In this lesson, we are going to talk about binary numbers and binary system. In binary numbers and binary system, the digits are 0 and 1. When we say binary, this means base 2, and the digits which are allowable in this representation are only 0 and 1, which is the same as 2 minus 1, base minus 1. For instance, in the system that you have used to, which is called base 10, you have digits which goes from 0 to 9, which is 10 minus 1. So you can represent any number you want, for instance, 127. Now, 127 in base 10, we represented as 127 and then 10 as subscript. This means 127 is in base 10. Now, in binary, as I said, the base is 2. So in that base, with only digits 0 and 1, the question is, how do you represent a number like, let's say, 17 in base 10? How do you represent it to a number in binary in base 2? To do that one, the process is very simple. You start dividing the number which is in base 10 by the new base, which is base 2, and collect all the remainders. And then you are going to start writing the number in the new system, starting from the last remainder to the first one. So let's do a couple of examples to see how simple this process is. Let's say I have the number 17 in base 10. And I want to represent this one in base 2. Let's come up with this notation of dividing 17 by 2 and continue dividing until the dividend becomes a number less than 2. 17 divided by 2 gives you 8. Do not say 17 divided by 2 gives you 8.5. 17 divided by 2 gives you 8. The remainder becomes 1. How do you find the remainder? You say 2 times 8 is going to give you 16. 17 subtract 16 becomes 1. Now continue. 8 divided by 2 gives you 4. Remainder becomes 0. Circle it. Then 4 divided by 2 gives you 2. Remainder is 0. Then 2 divided by 2 gives you 1. Remainder 0. Now this 1 here, the last one, because it's less than 2, we are going to stop and we are going to circle it. Now start writing the new number in base 2 from the last remainder to the first one. So I'm going to say 17 base 10 is 1, this one. The next one is 0, 0, then 0, 0, 1 in base 2. So we are just converted a number in base 10, which is 17, to a number in base 2, which is 1, 0, 0, 0, 1. Let's do another example. Let's say in this example we have to change 310, which is in base 10, to a number in base 2. How do you do it? Again, we are going to start dividing by 2. 310 divided by 2 is going to give you 155, and the remainder is going to be 0. Then 155 divided by 2 is going to give you 77, remainder 1. Because 77 times 2 is 154. So subtract 154 from 155, it's going to give you 1. Now we are going to divide 77 by 2. We get 38. So 38 times 2 is 76, so remainder is 1. Now 38 divided by 2 is going to give you 19, remainder is 0. Now 19 divided by 2 is going to give you 9, and the remainder is 1. 9 times 2 is 18, subtract 18 from 19 is going to give you 1. 9 divided by 2 is going to give you 4. 4 times 2 is 8, subtract from 9 is going to give you 1. 4 divided by 2 is going to give you 2, remainder is 0. Then 2 divided by 2 is going to give you 1, remainder 0. And 1, since it's less than 2, we are going to stop. So we are going to write the new number starting from the remainder at the bottom to the remainder at the top. And that's going to be the number in the new base. So we are going to say 310 in base 10 is 10011 0110 in base 2. So far, we talked about how to change a number from base 10 to base 2. The question is now how to change a number in base 2 to base 10. Give you one example. For instance, if we say a number is given in base 2 as 110, what is the same number in base 10? The rectangle represents the number. To do that one, we go back to decimal representation and see how that number can be written with the base and exponent. For instance, if I say 219 in base 10, this can be written exactly the same way as 9 times this number, 10, which is the base, exponent position of the digit minus 1. The position of digit 9 is 1. This is the first position. 1 is the second position, and 2 is the third position. So I can write 9 times 10 exponent 1 minus 1 plus 1 times 10 exponent. 1 is in the second position, so 2 minus 1 plus 2 times 10 exponent, third position minus 1. Now, 10 exponent 1 minus 1 is 10 exponent 0. So this is 10 exponent 0 plus 1 times 10 exponent 1 plus 2 times 10 exponent 2. Now, you remember from your math, 10 exponent 0 is 1. Any number exponent 0 is 1. So 9 times 1 is 9 plus 10 exponent 1 is 10 plus 1 is 10 plus 10 exponent 2 is 100 times 2 is 200. Add them up. 200 plus 10 is 210 plus 9 is 219, which you get the same number, which is what we started with. Give you another example. Let's say 17. I can write 17 as 7 times 10 exponent. This is the first position, so 1 minus 1 plus 1 times 10 exponent. This 2 is position 2, so 2 minus 1, which is 7 times 10 exponent 0 plus 1 times 10 exponent 1. 10 exponent 0 is 1, so 7 times 1 is 7, plus 10 exponent 1 is 10. 10 times 1 is 10, which is 17. We use the same idea for binary. Just remember that these tens, the bases, are the base of our numbering system. So this means that in binary we are going to change all these tens, these bases, to 2 now. In the next example, let's convert a number in binary to decimal. Let's say the number in binary is 101 in base 2. How do you change this one to base 10? Very simple. 101, this 1 is in position 1, so it becomes 1 times 2 exponent 1 minus 1 plus. This 0 is position 2, so it's going to be 0 times 2 exponent 2 minus 1 plus. This 1 is position 3, so it's going to be 1 times 2 exponent 3 minus 1. Now, this 1 minus 1 becomes 0, so 1 times 2 exponent 0 plus 0 times 2 exponent 2 minus 1 is 1 plus 1 times 2 exponent 3 minus 1 is 2. 2 exponent 0 is 1, so 1 times 1 is 1 plus 0 times anything is 0 plus 1 times 2 exponent 2 is 4, so it's 4. 1 plus 4 is 5. So we say 101 base 2 is 5 base 10. Now, remember that position 1 is going to be 2 exponent 1 minus 1, which is going to be 2 exponent 0. So position 1 is going to have a multiplier, which is 2 exponent 0. Position 2 is going to have a multiplier, which is 2 exponent 2 minus 1. Position 3 is going to be 2 exponent 3 minus 1. And so forth. Position 4 is 4 minus 1. And so forth. Now, 2 exponent 0 is 1. 2 exponent 2 minus 1 is 2 exponent 1, which is 2. 2 exponent 3 minus 1 is 2 exponent 2, which is 4. Automatically, if you look at the pattern, we started with 1, then we doubled it because base is 2, so it becomes 2. Then again, you double it. 2 times 2 is 4, so the next one has to be 8. 2 exponent 4 minus 1 is 2 exponent 3, which is 8. So the next one is 8 times 2 is 16. The next one is 32, and so forth. This means instead of writing 2 exponent 0, 2 exponent 2 minus 1, just remember these numbers: 1, 2, 4, 8, 16, 32. And multiply each digit of the binary number by these multipliers. Give you one example again. Let's say we say the number in binary notation is 1101 base 2. What is this number in base 10? Very simple. This 1 is going to be multiplied by this 1. So we're going to have 1 times 1. This 0 is going to be multiplied by 2. So we're going to have plus 0 times 2. This 1 is going to be multiplied by 4. So we get plus 1 times 4. And this 1 is going to be multiplied by 8. Plus 1 times 8. Add them up. 1 times 1 is 1, plus 0 times any number is 0. So 0. Plus 1 times 4 is 4. Plus 1 times 8 is 8. So 8 plus 4 is 12, plus 1 is 13. So we say 1101 in base 2 is the same as 13 in base 10.